So up to the last lecture, what we had covered was pretty much sampling theory for one-dimensional continuous signals and discrete sequences, and we related the two to each other through their frequencies. What our goal going to be now will be that we look at similar versions of sampling theorems for multidimensional signals. So previously we had looked at continuous signals which were in Rn, in L2R, and discrete sequences in L2Z. And these are called one-dimensional signals because they are just function of one variable. Signals or sequences. And our goal now is to extend that idea to multidimensional signals and sequences. So let's first try to see what do we mean by multidimensional signals. And for that, we will focus on first examples of two-dimensional signals. Two-dimensional signals, which we will often write as 2D signals and sequences. So when I use the word signals, I am not going to necessarily make the distinction that it's continuous or discrete. Now in 2D time, we are not going to call our signals as continuous time because there is no notion of two-dimensional time. So we will just use the word two-dimensional continuous signal or two-dimensional discrete sequence. Okay. So let's look at a continuous 2D signal. So 2D continuous signal is, for example, the class is called L2R2, which is a class of all two-dimensional functions, essentially functions which are made up of two variables, and they are just like the one-dimensional case, integrable, square integrable with the integration less than infinity. So you have f of x, y. Now you have two variables, and again we are skipping the t because time in two dimension doesn't make sense. So all those functions whose integration, two-dimensional integration, absolute value squared dx dy, that is less than infinity. Okay. Now, what is an example of that? An example of that will be a scene in front of our eyes, for example. So I'm looking at this object in front of my eyes, this image, right? And I can effectively say that it is a function of intensities that I am looking at, that my eye is looking at, where x corresponds to the x-axis and y corresponds to the y-axis. So any scene that I look at in 2D, that's like a two-dimensional signal. A discrete example of a 2D discrete sequence the sequences that we work with, we will call them L2Z2, okay, which essentially means that two variable functions which are square summable. So I have a function or a sequence fmn. It is a function of two variables m and n, and if I sum them over all of these indices over m minus infinity to infinity, n minus infinity to infinity, absolute sum, then that is less than infinity. That is less than infinity. It's just a generalization of the one-dimensional L2 sequence class that we studied earlier. An example of that will be something that you can relate more closely, which is a grayscale image inside a computer. So if you think of a grayscale image inside a digital system, inside your computer, your iPad, iPhone, then it's essentially a two-dimensional object, and it has pixels, and each pixel takes some value between 0 and 255. It's grayscale, right? So you have these pixels, and you can say that this is my, for example, N, and this is my M. Okay. So relating to a two-dimensional discrete sequence is pretty easy. Again, we'll focus only on the case of things that are finite energy, whether in continuous time or discrete time. Similarly, you can go beyond 2D. You can say, I want to look at three-dimensional images, three-dimensional signals. So the one class of continuous signals, again, it's finite energy, which we now write as L2R cubed. Okay, which is defined as now a function of three variables, f, x, y, z, where x, y, and z belong to R, that's why R cubed. And if I take the triple integral and I take the absolute value of this function, I square that, dx, dy, dz, that is less than infinity. An example of a three-dimensional signal will be temperature variations, temperature signal in a 3D volume. Effectively room. So if I think of this room in which we are sitting as a three-dimensional object with x-axis, y-axis, and z-axis, then at every point in this room, for every value of x, y, and z, I have some temperature value, which I can call fx, y, z. So it's a three-dimensional signal. Similarly, for the class of discrete sequences, the ones that we are interested in, they are called L2 of z cubed, which is simply the collection of all the sequences which are given by three variables. I'll call M and R. You can use some other term, such that if I sum them over all of these indices, M and R, f of M and R, absolute value squared, that is less than infinity. Okay. And an example of that from our earlier 2D case will be a grayscale video. Video inside a computer. So what is a video? A video is nothing but a collection of images which are played very fast. They are called frames in the language of videos, right? But if I think of this video stored, this is effectively stored like this, right? I have different images, and so I can call the x and y axis of these images, which are just discrete valued grayscale images, as m and n, and then I can call this as r, the dimension for the time. So these are examples of 2D and 3D signals. We can extend them to multidimensional signals, 4D, 5D, 6D, which you may not be able to comprehend right now, but there exist many examples where you basically, if you collect enough things, right, then you effectively have multidimensional signals which go beyond 3D. So if you add, for example, we talked about only grayscale. If you add the fact that you have images which are colored. Now, how are colored images? You can represent them. You can say for each color, I have two-dimensional image. In your computer, for example, you use the RGB format, for example, which is that a colored image corresponds to a two-dimensional image which has values related to the intensity of the red color, then another image which has values related to the intensity of the green color, then another image which is related to the intensity of the blue color. And you put them on top of each other and you see your colored image. So multidimensional signals can be generalized from 2D, 3D finite energy signals to MD, but we won't go that far. We'll try to stay within the two-dimensional space most of the times. Now, if we are going to talk about sampling of these multidimensional signals, since we have already covered the sampling theorem under the subspace model, it turns out same analogies exist in these multidimensional worlds because nothing changes. All these signals that we have talked about, so L2R, L2R squared, L2R cubed, and so forth, they are all, the reason we studied them, they are all Hilbert spaces, which means that notions of inner product and norms and all those things that we studied for the sampling based upon the projection formula, they are well defined. Okay, so if we want to say that how to sample a multidimensional signal, we can actually go back to the sampling formula, the general sampling formula that we had derived, and we can work with that version. So for example, if we say that focus on, let's say, L2R. So we focus on L2R2, which is space of all finite energy two-dimensional signals. Okay. So to derive a sampling theorem for this two-dimensional space, the first thing we need is some sort of a model for our signal, and the first model we could say is that we have a subspace within L2R. So say that S, which is a subset of L2R2, is a subspace of L2R2, and assume that your signal f of xy belongs to this subspace. Okay. So that's the first step when we are talking about sampling theorems for any kind of signals, one-dimensional, multidimensional. What do we believe our signal acts like or behaves like? So the general subspace model is, we say we have a subspace of our general space. So for two-dimensional signals, we just say we have some subspace of finite energy two-dimensional signals, and we say our function belongs to that subspace. Well, then the next step that we have already done many times, even though we did it for one-dimensional, the same thing remains true in the case of multidimensional, or in this case two-dimensional. Find an orthonormal basis of S, which I'm going to write as phi of L comma K xy. L comma K go from -infinity to infinity. So I'm talking about the notions of basis and orthogonality. The first question we should be asking ourselves is, of course, what is the notion of inner product in this L2R2 space? It turns out the extensions of the inner product in finite energy signals is very similar to what we had for one-dimensional. So if fxy and gxy belong to L2R2, then we define the inner product between f and g. How did we define it in one-dimensional? We took their integration and we just multiplied them, took the integration of them, integrated over the whole range, R, which was the real line. In this case, we will integrate over R2, minus infinity to infinity and minus infinity to infinity. The other stuff remains the same, f of xy, g of xy, dx, dy. Okay? And if I want to extend it to L2R cubed, I just add one more integration. Okay? It's the same notion that you see in one dimension. So we find the orthonormal basis of S, and then we have the projection formula then. Now, from the perspective of vector spaces, the projection formula doesn't change. The projection formula is always given by, if you want to do f tilde approximation of, if you want to take a signal f, you want to project it onto the subspace, the formula is the same. You take inner products of your basis elements with your function, and then you multiply them with the basis elements. So it will simply be, I take L minus infinity to infinity, K minus infinity to infinity, take the inner product of F with phi of Lk, and then I just multiply that with phi Lk xy. Okay? And if you remember your projection formula, whatever this comes out, we say that those correspond to the samples of our signal. Okay? So effectively, if you want to do sampling in higher dimensional spaces beyond one dimension, if you want to do sampling in 2 dimensions, it's, at least in an abstract setting, it is exactly the same operation. You take your function and you take its inner product with your basis elements. Now, in a non-abstract setting, you have to expand the definition of that inner product. So the samples, if you are given fxy, you simply take that and you take the integration of that with the phi Lk's, and at the output, whatever you get, you call those your samples. Right? You can call them FLK for every phi Lk. Okay? That's sort of the architectural view of how you will do the sampling. But in terms of an abstract notion, the sampling, even if my function now became 3-dimensional, as long as I had basis for these 3-dimensional signals, the samples will correspond to just taking the inner product of my 3-dimensional signal with the basis elements. The inner product now corresponds to, of course, threefold integral. So actually this integral should be twofold. So that is the general notion. Now that can be related to a specific case. We can talk about, for example, sampling of, let's say, 2-dimensional band-limited signals and all those notions, and we can make this concrete. But the general abstract sense of what sampling for higher dimensional signals, 2-dimensional, 3-dimensional, 4-dimensional signals mean The abstract setting remains the same. You take the inner product with your basis elements. Okay. Now, just in the case of one-dimensional signal where we really were interested in the setup where the basis elements were given by shifts of just one function. Okay. In two-dimensional and higher dimensional signals too, we are most interested in the case where the basis elements are simply given by shifts of any one function. Why? Because in that case, these inner products can simply be implemented using a two-dimensional filtering followed by two-dimensional sampling, point-wise sampling. Okay. So let's look at the case, special case. Phi Lk. So let's see, we are given some function phi of x comma y in my subspace, and suppose that phi of Lk x comma y is simply equal to some shifts of my function in x dimension and some shifts of my function in y direction. Okay. So a two-dimensional function, you can shift it just like the one-dimensional signal. You shift it on one axis. A two-dimensional signal, you shift it on one axis by an amount Lx, and then you shift it on another axis by an amount Ly. So if this is your two-dimensional signal, let's say this is, I'm not plotting the 3D, so this is, let's say, your two-dimensional signal, right? Where the dark, this darkness represents the value of the signal, okay? And let's say that this is x and this is y. Then shifting this by Lx means that I first move this whole thing Lx units in the x direction, okay? So let's say that this is my Lx. So I move whole this thing at Lx, and then I move it up by ky. Okay? So effectively, my center becomes here, and this shift, it will look like this. Right? So I shift it in x direction, and then I shift it in y direction. It's exactly analogous to one-dimensional case. Now you are doing two shifts. Okay. If of course the k was 0, your shift in y direction was 0, then you are only doing shift in one direction, x direction. So we are assuming that all of my basis elements are nothing but shifts of my one function in x and y direction. Why is that good? Because in that case, we can show, in that case, in a product of f with Lk can be implemented just like in the one-dimensional case, can be implemented using a two-dimensional filter and point-wise sampling. Okay. So let's first figure out what do we mean by two-dimensional filter. The notion is exactly the same in one dimension. Filtering effectively means that you convolve with some impulse response. You convolve with some function. That's the filtering operation. Okay. The filtering operation for that you have to understand the notion of 2D convolution, which is exactly the same as one dimension with just an extension. So if I am given one-dimensional signals, fx and gy, the convolution is given by f of, let's say, tau 1, g of y minus tau 1, d tau 1, right? This is my one-dimensional convolution expression, which means that you simply flip your function and you slide it by y units of time, you integrate it, and that's your output. So flip and slide rule. So in 2 dimensions, it's exactly the same expression. Let's say I'm given 2-dimensional signals, f of xy and g of xy. Now I will do 2 integrations, minus infinity to infinity. And I have f of tau 1 and tau 2 and g of x minus tau 1 and y minus tau 2 d tau 1 d tau 2. It's in the one-dimensional case, I should have used x here. Okay. So x and x. Okay. So if you stare at the 2 expressions, they're exactly the same. What is now happening that you are flipping your 2-dimensional signal, okay, in x and y dimension, and now you are shifting it in both x and y dimension by amount x and y. Then you multiply the 2 signals, and then you take their two-dimensional integral. Okay? And why convolution? Because just like in the case of one-dimensional case where we call things as linear time invariant, in 2-dimensional systems, the term that is used is linear shift invariant, which means that even if you shift your functions, the output just gets shifted. Okay? And the input-output relation in that case of linear shift invariant systems is described by the convolution expression. So we'll come back to that notion, but right now all we are concerned with is what is 2D convolution. This is the formula for 2D convolution. And what we want to argue is that if your basis elements are given by shifts of some one function, then just like in the one-dimensional case, you can carry out this inner product by doing first filtering, which is, when I say filtering, that means 2D convolution, and sampling, pointwise sampling in the 2 dimensions. Okay. So what I claim is that if you have that your basis elements are shifts of one single function, then the inner product between your basis elements, Lk, can be implemented as follows. You take your f, okay, and then you convolve it with phi of xy, 2D convolution now, because I'm writing 2D functions. And then at the output of that, whatever you get, you sample that output at every nx and my units of time, units of space. Okay, where capital X is some number, just like we had capital T, capital X is some number, and capital Y is some number. Okay, whatever function comes out of this, you just sample it, and that will be your inner product. I guess since I'm using L and K here, let me switch to L and K here. L and K. So that is what we want to argue. Let's look at that. So let's write down this. Again, it's 2D convolution, minus infinity to infinity, minus infinity to infinity. This is just the inner product. F of, I'm going to use dummy variables so that we don't get confused with the notation. F of Rs, phi of L comma K Rs, okay, dr ds. Now I'm going to write down what I mean by phi of Lk in this case. F of Rs, phi of R minus Lx, okay, S minus Ky, dr ds. That is my assumption that my phi Lk is simply given by shifts of some function. Now I can write that as f of Rs and phi of minus Lx minus Lx plus R, minus Lx minus R, and minus Ky minus S, dr ds. I made a typo here. This should be minus phi x and minus y, phi minus x and minus y. Now if you look at this and you compare it to your 2D convolution expression, right? So you have R here, S, tau 2, these are all dummy variables. You have minus Lx minus R minus Ky minus S, right? What this means is that this is equivalent to convolution between x, y, and phi of x, y, minus x and minus y. And then I set x comma y equal to Lx and Ky. Okay. So I simply do the convolution with these reversed versions of my signal, my basis elements, the function that generates my basis elements. And then if I replace x and y by Lx and Ky, which is equivalent to sampling this function. So I sample this in 2D. Whatever comes out of this, right, it's going to be a two-dimensional function. So convolution of two-dimensional function is going to be another two-dimensional function. And what I'm doing is I'm now taking the samples of that function every x units in x direction and every y units in y direction. Okay. Again, if this sounds too confusing, just try to relate back to the problem of one-dimensional sampling that we talked about. One-dimensional sampling involves filtering operation followed by point sampling. Two-dimensional sampling exactly has the same formulation, that it involves a filtering, but now filtering is two-dimensional, followed by two-dimensional point sampling. Okay, so that is just the general way you will do sampling of two-dimensional signals, and you can do the same for example, three-dimensional signals and four-dimensional signals. The definition of convolution easily extends to more than 2 dimensions. It's exactly the same expression. You keep on adding one more variable. You keep on doing these shifts. It's very simple to extrapolate it to other cases. Okay? And the basic notion stays the same. You filter it with the function that generates your basis elements, and then you take samples of your multidimensional signal in all its dimensions. Now, what we want to talk about, though, is a very special case of a two-dimensional signal so that we can try to better understand these concepts, because they may sound very abstract to most of you. You may not have seen two-dimensional sampling before at all. So let's step away from this abstract notion and let's talk about a concrete case of a two-dimensional signal class, which is a subspace, and we'll see what does all of this look like in that case. So let's make this discussion now a little bit more concrete by talking about the case of two-dimensional band-limited signals. So what we now want to talk about is a more concrete example of sampling of two-dimensional signals. And the example is that we will say the space S, which is the subset of L2 R2, is a space of two-dimensional band-limited signals. Now, there is an informal understanding of what does a band-limited signal mean in two dimensions, and there is a formal understanding. So let's first talk about informally. What does this mean? Recall, what does band-limited signal in one dimension mean? What it informally means is that your signal doesn't wiggle, doesn't change at too high a rate. There's some maximum frequency present in your signal. It can't change too fast. Okay? So it's exactly the same notion that if we look at the 2D signal in any direction, then it does not change too fast. For example, let's think of this plane, and let's say you have an impulse right sitting at the origin. So your fxy is simply delta of xy, which is a two-dimensional Dirac delta. Right? This is not a band-limited signal. You don't have to have any theory to be able to conclude that, because no matter which direction I go in, let's say I go from this point to this point, it is zero, and all of a sudden it goes up to infinity and comes back. Right? So the signal changes very fast. If I go from here to here, this is supposed to cross from the middle. If I go from here to here, once again the signal changes very fast. So this is a signal which changes very rapidly in these two dimensions, and so it's not going to be a band-limited signal. Okay? But there is also, just like the one-dimensional case, there is a formal definition of band-limited signals through two-dimensional Fourier transforms. So there is a formal definition of band-limited signals of 2D BL signals relies on the 2D Fourier transform. So just like the one-dimensional Fourier transform tell you which frequencies are present in your signal with what quantity. Right? If you have a one-dimensional Fourier transform, let's say, so the analogy is, let's say you have x of t and you get x of j omega, and you say that x of j, let's say 2 pi 10 to the 3 is 10 to the minus 6, a very small number. What does that say? That the 1 kilohertz frequency in that signal is almost non-existent in that signal. Right? That's effectively what Fourier transform is teaching us. It is telling us which frequencies are present with what kind of scale. Right? So a 2D Fourier transform is defined in a very similar fashion. It tells us what two-dimensional frequencies are present at what magnitude in the signal. Okay, and we'll take a look at examples of what do we mean by two-dimensional sinusoids or sequences, but let's first look at a formal definition of Fourier transform, two-dimensional Fourier transform. So the assumption is, just like in the 1D case, Fourier transform is defined only for L2R. In the 2D case, it is only defined for L2R2. So if f of xy belongs to L2R2, then the Fourier transform in radians per second of f is defined as f of j omega 1, j omega 2, minus infinity to infinity, minus infinity to infinity. It's exactly the analog of one dimension where you just extend the dimension and add the same things. So you get f of xy e to the minus j omega 1x plus omega 2y dx dy. Okay. This, of course, is a two-dimensional. This is a two-dimensional sinusoid. With frequencies, with x frequencies of omega 1 and y frequency of omega 2 radians per meter, or whatever unit you want to choose. Okay. So this is the formal definition of a Fourier transform, and there is again an inverse Fourier transform definition, that f of xy is given by 1 over 2 pi. Now, because you are in two dimension, you actually get a power of 2 here. Okay? In the 1D, you just get 1 over 2 pi. Again, two integrals, minus infinity to infinity, minus infinity to infinity, f of j omega 1, j omega 2, e to the j omega 1x plus omega 2y d omega 1 d omega 2. Exactly analogous to the one-dimensional case. And if you stare at it, what this says is that your signal is made up of, so what does integration is nothing but basically a summation, which is sort of, you can think of it as, if you think of the Riemannian integral, it's basically very summation taken at a very small scale. Right? So what this is saying is that your f of xy is made up of these two-dimensional sinusoids of frequencies omega 1 and omega 2, and the amplitude of those sinusoids is given by the 2D Fourier transform. And your signal is nothing but a collection of all of these two-dimensional sinusoids. Okay? So effectively, if I say that f of j let's say 2 pi 10 to the 3, and j 2 pi, let's say 10 to the 4, is approximately 0.0001. Okay? This will mean that this signal has the x and y frequencies of 1 kilohertz, and now I'm using the hertz term in a general fashion. Technically, hertz is defined in terms of the time duration. So, but we'll stick with the hertz aspect. And 10 kilohertz, that sinusoid with x frequency 1 kilohertz and y frequency 10 kilohertz, that is almost non-existent in your signal. Okay. So just like 1D Fourier transform tell you what kind of frequencies are present in your signal, 2D Fourier transform tell you what kind of frequencies, now two-dimensional frequencies are present, two-dimensional sinusoids are present in your signal. And the definition of the band-limited signal will be just like in the case of 1D, a band-limited two-dimensional signal will be the one whose Fourier transform becomes 0 after a certain value of omega 1 and after a certain value of omega 2, which means that the signal does not have too high frequencies neither in x direction nor in y direction. Okay? So that's the technical definition of 2D Fourier transform. We'll now take a look at, for example, what do these 2D sinusoids look like to give you a sense of frequencies in x and y direction so that you can relate it better, visualize it better. Okay, let's take a look at some example of 2D sinusoids to help us better understand the concept of what does it mean to have two-dimensional sinusoids with frequencies in the x-axis and the y-axis. So right now I'm taking the area from -2 to 2 in x-axis and -2 to 2 in y-axis. So let's take a look at sinusoids which have 0 Hertz frequencies in both x and y. Well, as you will expect, it's going to be just a constant signal, but in 2D, it's a plane. It neither changes in x direction nor changes in y direction. Okay? So now let's go further and take a look at the case where your x-axis frequency is 1 Hertz, but your y-axis frequency is 0 Hertz. Now, this is what the 2D sinusoid will look like. If you look at this way, and you go from this direction to this direction, right? Take a slice and go through. Your signal is changing. It has change going through that direction, but it has no direction change when you go in the other y direction. Okay? If I write it like this, it will be better for you to visualize it. If I go from here to here, right, in the x direction, then I have that the signal, the sinusoid is varying with some periodicity. Okay, it's a cosine that I'm drawing. But if I go along any line in this direction, in the y direction, it's a constant because that frequency along the y-axis is 0. I'm using 0 Hertz in the y direction. Okay? So this is the case of when I have x-axis is 1 Hertz, y-axis is 0 Hertz. Now let's look at the other case, which is now x-axis is 0 Hertz and y-axis is 1 Hertz. Now if you go along the y-axis direction, you see signal changing, but if you go along the x-axis direction, the signal never changes. Again, it may be better if we look at it this way. Okay. So if I go now in the y-axis direction, it changes at a rate of one cycle. Okay. Whereas if I go in the direction of x-axis, any line I draw in the direction of x-axis, it remains constant. That's a 2D sinusoid with frequency 1 Hz in the y direction and 0 Hz in the x direction. Okay? And 2D Fourier transform says that your signal is made up of an infinite number of such sinusoids with different x and y frequencies. Let's go forward. Let's take a look at sinusoid, which is both 1 Hz in x direction and y direction. This is what it looks like now. Okay? You can go from either x to y or y to x. You will incur the same rate of change. If I take a slice along x to y from in the y direction or x direction, I will incur the same change. If I again look at it this way, right, you see these nice diagonals, which means that basically both x and y axis frequencies are same. Okay, signal changes if you go from top to bottom or you go from left to right. Okay. Let's take a look at now a 3 and 1. So both are changing, but my x is changing at a faster rate. Okay, and again it will be much better if I look at it this way. So if I go from left to right, my signal changes faster. I have more of these bands, which means I have a higher frequency. Okay, but if I go from top to bottom or bottom to up, it does change because it's a 1 Hz frequency, but that rate of change is not that high. It's much slower than the 3 Hz. I can now do the same with 6 and 1, and you will compare that the rate of change. So this is 3 Hz in x and 1 Hz in y. This is 6 Hz in x and 1 Hz in y. If you see any line that I draw from top to bottom, the rate of change will be the same because it's 1 Hz in the y direction. But in the x direction, when I go from 3 Hz to 6 Hz, my rate has increased. Okay? And similarly, I can do the same now by increasing the frequency in the y direction and keeping it small in the x direction. So this is now x is 1 Hz and y is 3 Hz. Compare that to this. Okay? This is y 1 Hz, x 3 Hz. This is y 3 Hz, x 1 Hz. It has sort of like the whole image has flipped, right? Now if you go from left to right, your rate is small because x is 1 Hz. The x frequency is 1 Hz. But your rate of change from top to bottom is 3 Hz, so that rate has increased now. Okay? And similarly, I can have a 6-1 case where 6 Hz in the y direction and 1 Hz in the x direction. So this is what it means to have frequencies in the x direction and y direction. And your 2D Fourier transform effectively says that any finite energy two-dimensional signal is made up of an infinite superposition of such sinusoids. Okay? And a signal which has higher frequency sinusoids means that that signal changes fast. You will see more fluctuations. And a signal that does not have higher frequencies will have lower fluctuations. If you want to think of, for example, take two shirts, one is striped and one is plain. The striped shirt, Fourier transform, it will have higher frequencies because if you go from one direction to the other, signal is changing fast. Whereas the plain shirt, it has 0 frequencies. Okay? So it's completely analogous to the one-dimensional case with a few things that you have to be able to visualize or understand. So having described the notion of then 2D frequencies, we can now relate to what does a 2D band-limited signal mean. So two-dimensional band-limited signals, let's call them band-limited to, now you have to define two frequencies now, X frequency and Y frequency. So we are going to say band-limited to omega n1 and omega n2. Okay? What does that mean? F of xy is band-limited to omega n1, omega n2, where omega n1 corresponds to the X frequencies, omega n2 corresponds to the Y frequencies. If its Fourier transform becomes 0 the moment you go above omega n1 in X direction and the moment you go above omega n2 in the Y direction. So if f of j omega 1, omega 2 is equal to 0 for all omega 1 greater than or equal to omega n1 and all omega 2 greater than or equal to omega n2. Effectively, if you look at the Fourier transform, which is itself a two-dimensional function, right? Fourier transform is a two-dimensional function. If you look at the Fourier transform, and let's say that your Fourier transform looks like this. Okay, it's a two-dimensional sort of spherical thing. What this band-limited means that beyond certain region in your omega 1, omega 2 axis, there is a rectangle of size omega 1 in one direction and omega 2 in the other direction. So this is a rectangle, this is omega n2, and this is omega n1, let's say. So beyond this rectangle, your Fourier transform is 0. Just like we could visualize, for example, the 1D Fourier transform, and we could plot 1D figure and say, oh, it's band limited if it becomes 0 after 2 points. Now in 2D, we say it is band limited if it becomes 0 after a point in x-axis and after a point in y-axis, in omega 1 axis and omega 2 axis. What it effectively means is that the signal does not have very high frequencies. Okay? And again, just like the case you did in the assignment, it's easy to show that the space of 2D band-limited signals, S, which is the space of 2D band-limited signals, that space is a subspace of L2R2. Again, it's a trivial proof, just like the assignment. You take two signals which are band limited in 2 dimensions, you add them up. You take their Fourier transform, you will still have a Fourier transform which is limited to the bands of the previous 2 signals. So you take 2 band limited signals, add them, you get a band limited signal, which proves that the space of band limited signals is a subspace. Okay. Now, if you talk about, so assume that S is band limited to omega n1 equal to, let's say, pi over x, and omega n2 equal to pi over y. Okay. I'm not using t pi over t because, again, we are in 2 dimensions. Using variables, 2 variables of time doesn't make sense. If S is band limited to pi over x in one direction and pi over y in the other direction, then actually you can show that then sinc of x minus nx over x times sinc of y minus n capital Y over capital Y forms a basis for S. Just like the case of one dimension, we had sinc t minus nt over capital T form the basis for one-dimensional band-limited signals. It turns out that these two sinks, which are separable effectively, they are products of two one-dimensional sinks. Okay? These two sinks combined form the basis for band-limited signals. They're orthogonal basis. To orthonormalize them, you will have to divide them by 1 over square root of x and 1 over square root of y. Okay? So you can actually go through all the tricks that we did to prove the sampling theorem for one-dimensional signals. We are going to sort of short-circuit that, and we are going to just assume that we'll work that out, and hopefully we'll be able to solve that problem in an assignment. But it turns out that if you are given 2D band-limited signals, okay, so there is a similar sampling theorem, just like the one-dimensional case. There is a Shannon-Nyquist sampling theorem for two-dimensional signals. The Shannon-Nyquist sampling theorem says which you can derive either using the projection formulation or using the same kind of tricks of multiplying your two-dimensional signal with a 2D direct comb and then looking at what happens to the Fourier transform and going through all that and showing that no superposition happens. You get multiple copies when you do that sampling, and no superposition happens if you satisfy certain constraint. But I'm going to directly write down that formula. So the Shannon-Nyquist sampling theorem says that if f belongs to S, which is band limited to omega n1 and omega n2, then f of xy can be recovered from its samples. Now we are going to talk about 2D samples. From its samples, which we are going to define f of mn equals to, or let's use f of nm, and m, actually in the sink it should be m, sorry. F of nm equals to f of nx and my. Okay. What this means is that you are given your signal and you take its sample. So let's say this is your 2D signal domain. I'm not plotting its value. You divide it into a grid in x-axis and in y-axis. So in x-axis, you take samples every x duration or spacing. In y-axis, you take samples every y spacing. Uniform samples. Okay? You take these uniform samples, every x spacing, every y spacing, then your signal can be recovered from these samples as long as omega n1 is less than or equal to pi by x, and omega n2 is less than or equal to pi by y. Equivalently, you can state that in terms of the sampling, x and y sampling rate. So you can define omega s1 equal to 2 pi over x, and omega s2 equal to 2 pi over y. So the condition becomes that the sampling rate in the x direction should be twice, the sampling frequency in the x direction should be twice the bandwidth in the x direction. So omega s1 should be greater than or equal to 2 times omega n1. And omega s2 should be greater than or equal to 2 times the sampling frequency in the y direction. Okay? That's what the Shannon-Nyquist sampling theorem states in the 2D, which is exactly the extension of the one-dimensional case. So you have no frequency. If you have high frequencies in y direction, then you better sample more in the y direction. So if your x direction has very low frequencies, you can have a lot of spacing in x direction, but your y direction must have small spacing if your y direction has high frequencies. Okay? And the reconstruction part of this is again given by the sinc interpolation, where we have now the 2D sinc. But that we'll start with that in the next lecture.